Hey, okay, so I'm going to try to be a bit quicker on this one. This is, I believe, section 1.4, and it's all about applying transformations. Now, you'll notice the letters are different. For instance, your book likes to use K here, and I like to just use A, B, C, D. You also notice that they put like minus signs in here with the X transformations, and that's just to remind you that X does the opposite. Um, and Y transformations are very straightforward. What you see is what you get. But I've also developed this very handy transformation tool in Desmos, which I'll put a link in the description. And this is for the sine curve right here, but we can make it for anything. Let's make it for a parabola. Okay, click on home, and boom, we're zoomed right in. And here's your standard parabola. And then I've done this. I've said, well, this is f of x. And here I've said g of x is going to be transformations of f of x. There it is right there. And notice that when the transformation happens outside of the f to the left of the f, that's a y transformation. And when it happens inside the f, that's an x transformation. Just as this is right beside the x, it's an x transformation. And this is outside the bracket, so that's a y transformation. So the a and the d are y transformations. Let's go straight to those. So a and d. What will happen if I change d? Well, d is simply at the end here. It adds on. It's just going to raise or lower my parabola depending on how much I add on. So if I add on 3, okay, there. The purple's the original, and the green is the new transformed one. It's simply been raised by 3. And if I lower it by -4, let's say, there it is. How do I prove it? Well, look at the vertex. The vertex is now at, oh, I accidentally did 3.9. The vertex is now -0, -4. So D is very straightforward. So let's go put it back at 1. You can also hit play here, and it'll show you what happens as it goes from 10 to -10. Just shows you it lowers and raises the parabola. So D is a y transformation, and it's a very straightforward y transformation. What happens with 1? Well, 1 is right here in front of it, and 1 is a stretch on the y. So if it's twice, if there's a 2, all the y values are going to be 2 times what they were normally. So it's going to be thinner, stretched vertically. There it is. The green is stretched vertically. And you might say to yourself, oh, that doesn't look like halfway between the y-axis and the purple line. And it's not. That's not how it works. The original value here is 1, 1. And if the y value is 2 times, that means the stretch of this one has happened up here at 1, 2. There it is there. Over here, the standard one on the purple line is 2, comma, where's the 2, comma 4, right there. So that means the stretch, what's 2 times that y value? It'll be 2, comma 8. So right up here, there's the 2, comma 8. So you can see all the values, all the y values that transformed are the 2 times as much as they were. And that's why it didn't go this way. It went up here. It stretched from here to 4 up to 8. And that's what's going on. It's stretched this way, vertically upwards by 2. So A and F are very straightforward. What happens is if this is negative, let's say if it's -1, boom, the parabola is the same size parabola, but facing downwards. Same with -2, it's facing downwards, but stretched by a factor of 2, 3, 4. Let's click play and see what happens. Okay, the y is the transformed parabola. And you can see as soon as it bounces down to the below the y-axis there, and above, that's when a is negative or positive. It's positive, 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 negative. And if you look at the a changing over here, you can see indeed that's what's going on. But it's still very straightforward. All my y values would be multiplied by that number if it's -8.67. All my y values from my original parent function are multiplied by -8.67. It's very easy to plot. So that means that 1, 1 became 1, comma, -8.67. Let's see if there's a 1 here at -8.67. Almost. Okay, there it is. See, 1, comma, -8.67. So all my original y values simply got multiplied by -8.67. And that makes it very easy if you know the standard y values or x values. If you know these 3 5 coordinates, you can easily translate them. And let's just not make it negative x point. Let's make it negative 4. So this is instead going to be 1 comma 1. What happens when we multiply our y by negative 4? 1 comma negative 4. It's going to be right somewhere around there. There it is. What happens to 2, 4 when I take that 4 and multiply by negative 4? It becomes 2 comma negative 16. So it's going to come down here. Almost. There it is, 2 comma negative 16. 0 doesn't change because when you multiply 0 by negative 4, it's still 0. And the same things happen here except on the negative side. So I'm going to get negative 1 comma negative 4. Somewhere around there. And of course negative 2 comma negative 16. Somewhere around there. So if you know your parent function quite well, and it should be easy to come up with 5 coordinates of any parent function, the transformations are also easy to figure out for y. And the nice thing is, no matter what the parabola, no matter what the function is, so if it's sine x, that transformation, and sorry, it doesn't look very good because of how it's drawn, but if we just go from 366, there, that'll do, and then just do this from minus 2 to 2, it'll be much clearer. There we go. The purple is the original. Purple's the original, and it gives you some standard values. We'd really just have to get rid of this one and do it again for some standard values. And some standard values would actually be 190, 180, 270, and 360. And you can see we get what we expect. And if you memorize these key 5 points, you can transform it. So what happens when my a in front becomes negative 4? Well, all these y values will be multiplied by negative 4. So instead of 0, 1, 0, minus 1, 0, let's see what happens. Oh, it flipped, and it became 90 comma negative 4. So the y value got multiplied by 4. 180 comma 0 because shares the point because 0 times negative 4 is 0. Then instead of 270 minus 1, it's going to be 274. There it is. And then finally at 360, it shares the same point because 0 comma 0. 0 times 4 is still 0. So you can see it flipped it upside down and stretched it vertically. So that's really a nice thing to have this consistent application. So what happens to the d? Here, I'll just run d, and you'll see my sine curve goes up and down, 10 up and 10 down as d changes. So y transformation is very easy to see. So we're going to go back to our standard, and we're going to go back to a parabola. So parabolas are just your most standard one to work with. Now, what about these in the middle? Well, unfortunately, with x's, the opposite happens, and I left it as plus just to show you what happens with c. If I do plus x plus 2, if I change my c to plus 2 down here, you'd think the whole thing will move to the right by 2, but it's actually the opposite. It'll move to the left by 2. So here I'll make my c. Oh, and it's set to 360 because the original one is a sine curve, but I can just make it minus 10 to 10. And step of 1. There we go. And now watch what happens when I change my c to 2. My whole parabola, which is the transform one, this green, moved left to the 2, so the vertex is no longer 0. It's minus 2 comma 0. And that's also still easy to do. All my x values, I subtract 2. So if I look at my standard values up here, here's my standard values. What happens when I subtract 2 from 1? I get minus 1 comma 2, minus 1 comma 1. The y value stayed the same. What about this one, which was minus 1 comma 1? When I subtract 2, I get minus 3 comma 1. So you can see the transformations are easy to figure out. If you know your original 5 points on the parent function, it is easy to do. Let's change this to minus to 4 to see what happens. The whole parabola moved left to 4. Let's do 5, actually. And there, these 4 points, 0 comma 0 will become minus 5 comma 0. 1 comma 1 will become minus 4 comma 1. So all my x values got 5 subtracted, and that's the opposite. You see plus, it would be plus 5 here, if I just put in plus 5. But it actually, instead of moving to the right by 5, moved to the left by 5. So it does the opposite. And that's something to keep in mind for your x transformations. Your x transformations will do the opposite. All right. Let's look at this here. You'd think if I put a 2 in front, all my x's will stretch by 2 to the right, but actually a 2 actually compresses it by a half. See, it got thinner. It didn't stretch the y values. So if it was 1 comma 1 here, what do you think the x value is if I multiply that by a half? It's going to be a half comma 1. Sure enough, there it is, 0.5 comma 1. Same with this one. What happens to the minus 1 when I multiply by half? It becomes minus 5.1. So you can see that this tool is very handy. And I'm just going to hit play on the b value. And what happens when the b is going to get negative? Flips. Oh wait, no, it doesn't flip upside down. It flips, it crosses in the y-axis. Why can't we see that? Well, because a negative reflection, when something's perfectly symmetrical around the y-axis, when it's negative, you actually can't see it unless it's also moved a bit to the left or the right. So let's see if I move it a bit to the right here. And then look what happens when this becomes positive. Oh yeah, that's right. You still can't see it because it's symmetrical around its new axis, which is over at minus 3. So you won't be able to see a negative thing, even though it's actually happening. Visually, when something is symmetrical along its vertical axis, you actually won't see negatives. Where you'll see it more is for something that doesn't have a symmetry. So here's the standard growth curve. Okay. And the standard growth curve is in try that. There we go. Is in green. And now let's look at what happens when this b in front becomes negative 1 instead of 1. Well, look at that. All the x values got multiplied by minus 1. And you might say, I thought you said it was a reciprocal of what's in front. Well, the reciprocal of minus 1 is still minus 1. Let's do it to minus 2. Now it's been stretched, compressed by a half, not by 2, and multiplied by negative 1. So that means 1 comma 2 is going to be half of that and negative. So it's going to be negative a half comma 2. There it is, negative a half comma 2. And that means up here, 2 comma 4, when I take that 2 and multiply by negative a half, it's going to become negative 1 comma 4. And you can see the reflection in the y-axis now because this was not a symmetrical function. It's easier to see reflections in the y-axis when it's not symmetrical. But it's important to understand what happens when this value in front becomes negative. It flips in the y-axis. And when this value in front of the whole thing becomes negative, it flips in the x-axis. So there's sort of an opposite there. The negative y value flips it in the x-axis. And that makes sense because all the y values become the opposite sign. So they go from up here to down here, and all the x values go opposite sign. So they go from over here to over here. And that's why it's flipping in the other axis. Take some time to understand it, and that's why playing with this thing is a good thing. So I'm going to let it play, and you'll be able to see it flip. But boom, it's back to the correct side because it's positive, and here it's going to go negative. It's on the other side now. Here it's going to go positive, and it's on the matching side. Here it's going to go negative again. All right, so let's let that go back to a normal value, 1, and let's look at the C value, or sorry, the A value, which is up front, and let that hit play. Oh, when it goes negative, it flips in the x-axis, and then comes back up when it's positive, and back down when it's negative. So you can see visually, these things help a lot, and you should use them. And then let's just let the D play. See, the D is the easiest one to understand. Up and down. So I hope that helps. And just remember, you can always change your function here, and this will adjust that function because it's got f of x right in it. And so study it. Understand what is happening here. And remember that the x's are the opposite. Now, your book uses slightly different notation. Your book likes to use k, and it even likes to put k as the reciprocal already. and then plus D, and then you see for some reason it doesn't do minus D, but it does do this one flipped around. It should be doing both. And then Y just keeps the same, and it uses A and C for Y values and D and K for X values, which is just a little extra confusing. And then how they explain it's a little confusing too. But just follow along. So let's state the transformations as shown here. Well, and notice here in this question they're just giving you a generic function, f of x, and they're asking you what happens when this happens to f of x. Okay, well, let's see what they did to it. What happens when you take f of x and you do this? Well, let's identify it first. Is it beside the x? No, it's not, so it's not an x transformation. Is it in front of the f? No, it's not, so it's not a stretch to the y. This here simply raises or lowers it by 1. So if I had a normal parabola, all the y values would be reduced by 1. So if I knew the original y values, I would just subtract 1 from them, and I would be able to plot the new ones down here. And very easy. Very easy once you get used to it, especially at spotting it. Okay, and what about this b here? Let's look. Oh, they give you two things. Well, let's identify what they are. First of all, is it right beside x in here? Yes, it is. Is it right in front of the x as opposed to out here? Yes, it is. Is there anything outside here? No. So these are both x transformations. So this one's going to move the whole function left or right, and this is not going to stretch it by 2, but compress it by a half because you take the reciprocal of that. So 1 over whatever is there. So that means, am I moving to the left by 1? No, I'm moving to the right by 1 because x values are moving to the right. And is it multiplied by 2? No, it's going to be multiplied by a half, which means I take all my x values and I multiply them by a half. You always do the multiplier first, and then add 1 to it to get the new values. So if I was talking about a straight line, which is 1, 1, 2, 2, I take all my x values, multiply by a half, and then add 1. So actually, this one doesn't change. It still becomes 2, 2. But this one, when I multiply by a half, becomes a half, and when I add 1, it becomes 1.5. 0, 0, when I multiply by a half, is still 0. But when I add 1, it's 1, 0. And then so on and so on. Now let's see if that's true. Let's take line as our function. And we're going to change our b to 2. And we're going to subtract by 1 here. So I'm going to make it minus 1 down here. And sure enough, I still have this as 9. It should just be a 0. And sure enough, the green line represents our transform line. There's one of the transformations. Notice it still shares 2, 2 as predicted. Here's 1.5, 1 there. And then these lines also get transformed. So this -1, when I multiply by half, is -0.5. And then when I add 1, it's 0.5. So there it is there. 0.5, -1. And this, when I multiply a half, becomes -1. And when I add 1, becomes 0. So it becomes the y-intercept. So you can see the green line followed all the transformation rules as shown, and they were all x values. They all did the opposite of what you would expect. You could also figure out the exact coordinates by following the rules, multiplying it by a half, and then adding 1 to all the x values, and keeping all the y values the same because there are no y transformations shown. Let's look at the next one. See, two things going on again, but they're two separate things. First of all, let's look at the -3. Is that right? 3 things going on. Yeah, the -3 is right beside the x. Then we got a -1. Is it right beside the x? No, it's outside the f. So that's a y transformation. That's an x transformation. What about this +2? Well, it's outside of that. So that's a y transformation, which means I'm going to take all my y values from the last of whatever function I'm working with. I'm going to multiply by -1, and then I'm going to add 2. Then I'm going to take all my x values, and I'm going to simply not subtract 3. I'm going to add 3 because it does the opposite. And I will be able to plot my new graph, knowing my parent graph, 5 points from my parent graph. I will be able to plot my new graph. But it's important to know what these all mean. Let's look at this next one, D. Okay, what's going on in this one? Well, the thing right beside the x is definitely affecting the x, so that's an x value, and then there's nothing there, and there's nothing there, but there is this minus 2 up here, so that's a y function, which means all my x values don't get multiplied by 4. X values instead get multiplied by a quarter. Now, some people might say it's going to be divided by 4, which is still true, but it's easier just to say it's multiplied by something and learn the reciprocal. Then all my y values are multiplied by minus 2. If you want to do that in 2 steps, that's fine. They get multiplied by minus 1 and then by 2. But it's much easier to just do that. Which means if I have all my original coordinates for my parent graph, I can just follow this rule for each of those coordinates, come up with 5 new coordinates that will fall correctly on the transform graph. All right, let's look at this one. What's happening with this one? It's E. Several things. So let's identify some y's. There's a y. There's a y. Let's identify some x's. There's an x and there's an x. So there's several things going on here. Let's look at what happens to the x values. Well, all my x values will be multiplied by minus 1 because you have to go first. And you might say, oh, no, you do the reciprocal. Yeah, but the reciprocal of 1 over minus 1 is still minus 1. And then you will not add 2, but subtract 2 because the opposite. And then all my y values will be multiplied by minus 1 because you always do the multiplication first, and then subtract 3 because what you see is what you get for y's. Which means if I have the 5 original points from the apparent graph, which I should have memorized, it's not hard to remember those 5 points, or even figure them out quickly using a chart. Then I can figure out all my new transformation points. And then finally, they're going to give you a really complicated one, like this. And you'll also discover teachers who give you transformations of transformations, which is kind of dumb, but so be it. So this one here is outside the f, so it's a y. That's inside the bracket, so an x. This is inside the bracket, so it's an x, and outside the brackets, so it's a y. So we got 4 different things going on. So all my y values, let's do x values first, are going to be multiplied not by a quarter, but multiplied by 4, the reciprocal of a quarter. And then I don't subtract 5, I add 5. And then all my y values are straight forward. I multiply by half, and then add 6. And if you follow this rule for your 5 basic points of your parent graph, you will find the 5 basic points on this new graph and be able to graph it. And that's all your teacher will want you to do. Now, what point was I going to bring up? Oh yeah, some teachers will present this internal thing, and they love doing this. Teachers just love doing this. They're not going to show you this part here. They're going to show it to you as this. And then you're going to say, oh, this gets compressed by quarter, and all the values get moved to the right by 5 quarters. But that's not true. You cannot have this quarter in front of the x and this minus number. It's got to be expressed like this up above. To express like that up above, I divide everything by a quarter, which is how you factor it out. And when I divide this by a quarter, it's the same as multiplying it by 4 over 1. And these cancel out, and you end up with this. And teachers love to write it down like this just to trick you. Over and over and over again. Every year they do that. And you've got to factor it out correctly, factor out this quarter to see that. You'll notice that the compression's the same. Or sorry, the stretch is the same. But the translation is not the same. It's 5 to the right, not 5 quarters to the right. Teachers love putting it down like this every year, every test. So don't get caught. All right, then they just ask you to do it from graphs and try to come up with the formula from the graph. And again, this is knowing an important part of knowing all your parent graphs and knowing where their basic starting points are. So let's see if we can, and they want you to, essentially want you to come up with a new formula. Identify the A, the K, the C, and the D in this formula that's based on this. A horizontal stretch by a factor of 2, vertical translation 3 up, and a reflection on the x-axis. So this is a totally different one. Okay, let's focus on what's y first. What are y values? The horizontal stretch is an x. Vertical translation 3 up, yep. Reflection in the x-axis is indeed a y value, even though you see the x-axis there. This is done by making a negative. So a, since there's no stretch, vertical stretch is -1. Vertical translation up just means we've moved the whole graph up by 3, and that's the c. So that means c is equal to +3. The only thing left is this x transformation, a horizontal stretch by a factor of 2. And you'd be tempting to say, well, that means there's no d, and you'd be correct, and you'd be tempted to just put a 2 where k is and say k is equal to 2. But that's not how you create a horizontal stretch. K has to be equal to 1/2 to create a horizontal stretch of a factor of 2. And that's the secret there. There is no d value. There's no d value because it didn't move left or right. It didn't translate left or right or horizontally. This one, they're going to give you a drawing. And they're giving you the parent curve, and they're asking you to figure it out. Well, there's several things that happen to this. Yeah, you could say it's a sine curve that was reflected, but it's easier not to. It's easier to notice that the axis here in orange is right here. That is, I'll do it in blue. That is the axis of that red sine curve. How do I know? Because there's an equidistance to the max here and here. I also can figure out that axis is down here at -2, so that means the whole curve was lowered by -2. So let's start with the sine curve and a, and then it's, I think they want k sine x plus c, do they want? Plus d, which means my d is -2. Then you'll notice that the amplitude is no longer 1. It goes from -2 all the way up to 1. So that means that amplitude is 3. That amplitude is 3. What controls amplitude? Vertical stretch. And where's a vertical stretch? It's in the y. So that means a is equal to 3. And that's very straightforward. Now, notice that the original period, so that means for a, I'm talking about y is equal to 3. We don't know k yet, and we don't know sine x plus c yet, but we do know -2. So notice it hasn't been shifted left or right. It indeed starts right here at 0. So there's no c, but does appear to be some sort of stretch, because the normal period of a circle is 360, and this one, to get a full period, I can just go from peak to peak. I can start here if I want and go all the way to here to see where it repeats, or I could go from bottom here, so the bottom here is about there, a little confusing, and so they're not quite good at giving me accurate numbers. There we go. Peak here is 540 all the way to this peak, which is, what's 270 divided by 3? 90. So that's 180. So -540 all the way to 180 is the same as 720, which means to go from 360 period to 720, I had to double it, which you'd be tempted to put a 2 in front of this k, but in actuality what you put is 1/2, which means the whole formula here, since the period doubled, is 3, open brackets, 1/2, nothing changed in the phase shift, so it didn't move left or right, -2. And that is the new formula. So if you can identify A, K, there's no C or D or whatever they use, but there is a D, -2. And if I use Desmos, you're going to discover that sure enough, y is equal to 3 sine a half x. Oh, I had to put that in brackets. A half x, and then lower it all by 2. And then we'll just put the axis there so you can see it easier. Sure enough, there's my sine. There's my new sine curve. And you're going to get used to radians soon enough. And my new sine curve is no longer 2 pi, it's 4 pi. And you can switch that to degrees and you'll see it much easier. And we'll go from this to 370 or 720. There we go. So I switched to degrees so you can see it easier. And there's the period right there. It ends at 720 and starts here at 0, 0. And here's the normal sine curve. Okay, there you go. And you can see it was all easy to see visually if you knew how to determine what amplitude is, what period is, if it was phase shifted, and if it was reflected, and if it was stretch. Stretch is amplitude, and D is always where the new axis is. So whatever this axis is, that's always going to be D for sine or cosine curve. 3, the 0.23 is on the graph of fx. Determine the corresponding correspondence. So you just have to figure out what the transformations are. It's the same rule that we were doing. I might have to take a 2-second break here. Okay, so we have the original point. We don't know the curve, but it doesn't matter. There's the original point. So that's an x and y value, and then we just have to figure out all the x and the y transformations given by this. So again, let's look at which are y's. So I'm going to circle the y's. That's a y, and that's a y. And now I'm going to circle the x's, or square the x's. That's an x, and that's an x. So going through what happens to the x's, all the x's are not multiplied by 2, they're multiplied by a half. And then not add 5, but subtract 5. And all my y values are multiplied by -2, so exactly as you see, and then lowered, or subtract 4. Which means I just follow that rule. So I take 2 here. 2 is my x value. I multiply by a half. What's 2 multiplied by a half? It's 1. And then I subtract 5. What's 1 minus 5? It's -4. So that 2 becomes a -4. Now I take this 3 and I follow these rules. I multiply by -2. What's 3 times -2? It's -6. And then when I subtract 4, I get -10. So I get -4 comma -10 is the new point on this graph. And you can see once you figure out the rules, you can just directly apply that to your x and your y coordinates to figure out your new x, y coordinates. And teachers are going to get tricky. They're going to give you the new one and ask you to figure out the original. To do that, you got to do these steps backwards, and you got to do it backwards in the same way that they were applied. So first you got to add 4 and then divide by -2 and then add 5 and then divide by a half to go backwards. Some of them are tricky, but right now they're just doing straightforward. Straightforward, you just follow the rules. Okay, next one. Practice. So they're going to give you a bunch of ordered pair and ask you to figure out what the new ordered pair is, much as we just did. And it's the same rule. And I might have to just call it quits for a second here, because I believe I have something on the stove. All right, but I'm going to give you an idea of just this one here. And then I'm going to follow the rule. Okay. And we're going to look at each rule separately. Let's look at this one. There's only one thing, is that if y are an x, it is a y, because it's in front of the f, and y's are straightforward. So that just means there's only one thing going on, and I multiply all my y values by 2. So the new coordinate is 2, 6. And then if I look at this one here, 4, 7, it becomes 4, 14. The x values don't change. And the -2 becomes -2, 10. And the -4, 6 becomes -4, 12. There, I've transformed each y value. These are all the new coordinates when I multiply when it transformed like this. Okay, what about this next transformation? And actually, I might as well keep all the coordinates out here. We'll just try to undo it all here. There we go. And I might as well keep all the coordinates out. What about the next transformation? Well, just follow the rules. The next transformation has only one again. What is it? I'm just going to move this out of the way. It is an x transformation. Are my x's moving left to the 3? No, they're moving to the right by plus 3, which just means the only transformation I apply here is I add 3 to all my x values. So I get 5 comma 3. 4 plus 3 is 7 comma 7. Minus 2 plus 3 is 1 comma 5. Minus 4 plus 3 is minus 1 comma 6. Notice the y values didn't change at all because there were no y transformations. Only the x values changed. Okay. And let's look at the next transformation. Again, they're going soft on you. There's only one transformation. Is it beside the x? No, it's outside the brackets. It's over here, which just means all my y values get 2 added to them. So I get 2 comma 5, 4 comma 9, minus 2 comma 7, and minus 4 comma 8, which essentially means the entire graph went up by 2. And over here it just means the entire graph was stretched by 2, and over here it means the entire graph was shifted to the right by 3. And that's it. That's pretty straightforward. All right, what about this one? They're starting to add more things at once. This one has 2 transformations. One of them is the x values. One of them is the y values. Let's redo that. So that means all my x values don't add 1, they subtract 1. But all my y values do as we see, so I subtract 3 from all my y values. So I get 1, 0. So I subtracted 1 and then subtracted 3. I get 3, comma 4. And I get minus 3, comma 2. And I get minus 5, comma 3. These are the new values. And all I did was subtract 1 from all my x's. And then subtract 3 from all my y's. And I got my new coordinates. So essentially the entire graph shifted to the left by 1 and down by 3. Is how you would verbally describe it. And your teacher will ask you to verbally describe it. What about this one? Let's have a look at this one. Well, this one's just got one thing going on. It's a reflection in the y-axis. Whoa, 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 that's beside the x. Yes, but the negatives are reflections. In other words, they use the y-axis as a mirror. It makes sense because all the y's, if they were positive, became negative. Or if all the x's were, negative, they become positive. That's what that does. It changes all the x values to the opposite sign, which is a reflection in the y-axis. Which just means multiply all your x values by minus 1. Whoa, 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 I thought you said it was reciprocal. Yes, but minus 1, the reciprocal of minus 1 is still just minus 1. So that's easy enough. Just change the signs of all your x values. So essentially all that happened is all the x values swapped with their opposite on the other side of the y-axis. So reflected in the y-axis. Now I use y-axis loosely because really it reflects in the whatever its axis is. But we use the y-axis for parent functions. And I'll explain that more later. Okay, what about the last one? The last one's this. And my mouse battery's getting weak. 2 transformations. You might say all my x values are multiplied by 2, but no, they're not. They're multiplied by half. And this is outside, so that means I lower all my y values by minus 1. So multiplying this by half, I get 1, and subtracting 1 from the 3, I get 2. Multiplying this by a half, I get 2, and subtracting 1 from the 7, I get 6. Multiplying this by a half, I get minus 1, and subtracting 1 from the 5, I get 4. Multiplying this by a half, I get minus 2, and subtracting 1 from the 6, I get 5. These are my new coordinates, and that's the transformations. So essentially everything got compressed on the horizontally by a half, and lowered. The entire graph got lowered or phased down by, translated downwards by 1, is how you put it in words. Pretty easy once you know the rules for those. Here they want you to state the parent function, and the transformations that were applied, and then graph. I'm not going to graph it. Use Desmos for that, but you can right away you can see the parent functions. That's a parabola. To see parent functions, just get rid of the numbers. Okay. See? You're going to keep this number because it's part of the basic equation. Right away you see the parent functions. Y is equal to x squared. Y is equal to absolute value of x. Y is equal to sine x. Y is equal to 1 over x, so that's a rational function. Y is equal to 2 to the x, so that's a growth function. And y is equal to the square root of x, so that's a root function. Boom, there's all the parent functions. What are the transformations? Let's identify them. This is affecting the x. It's inside the bracket, so it's not moving everything to the right by 1, it's moving everything to the left. So all your x values, the entire graph transforms to the right, left by 1. So you would take your normal parabola and whatever your parent points are, you would just subtract 1 from all the x values and graph it that way. Your teacher's definitely going to want you to graph. What about this one? Is the 2 inside beside the x or outside? It's outside, so that means all my y values have been vertically stretched by a factor of 2. That means you would take your absolute function, you'd take your 5 key points, and you would multiply all those y values by 2, and you would keep all the x values the same. So essentially it's going to be a thinner v. Bad. And that's how you would do it. What about this one? Well, this is definitely beside the x, and this is definitely not. So that means all my x values are multiplied by a third, and then all my y values are added 1, which means I'm experiencing a horizontal compression, and I'm translating everything upward by 1. So you would draw your original sine curve, figure out your key 5 points, multiply all the x values by a third, and then add 1 to all your y values, and you will have your new graph. You'll discover it's got a third of a period. What is the third of a 360? It's 120. So you'll discover this whole thing completes after 120 degrees. And with that, shift up, all the maximums and the minimums will go up by 1, as will the axis. What about this one? What's going on with this one? Well, that's just a rational function, and it's been raised by 3. So all the y values would just add 3 to it. So if you knew the basic 5 points for the rational function, you just take all the coordinates, you'd leave all the x values the same, and all the y values you would just add 3 to, and now you can graph it. You just kind of join the points knowing on what the basic rational function looks like. What about this one? What's going on? Is that 0.5 beside the x? Yes, it is. That 0.5 is behind the x, and that is just the base, so nothing's happening with it. But all the transformation that's going on is a horizontal stretch by a factor of 2, not a half. The reciprocal of 0.5 is 2. Do your calculator if you don't understand that. Which means all my x values are multiplied by 2. So if I know the 3 basic points from the original parent graph, I keep all my y values the same, and I just multiply all my x values by 2, and I will have new coordinates, and I can join them, and it'll still never reach the x-axis because it wasn't raised or lowered. So the x-axis is still the bottom asymptote, and it goes on forever up there. What about this one? This one is definitely x because it's all inside the square root, and all my x values will not be multiplied by 2 but multiplied by half, and then you would add 6 to all of them. So you would take all your original points from your normal parent function, you'd leave the y values the same, but all the x values you multiply by a half, and then add 6. So 0, 0 is 1. That 0, 0 becomes 6, 0. 1, 1 is a point. When I multiply by half, I get 0.5, and I add 6. It becomes 6.5, 1. 4, 2 is a point, which means that if I multiply by half, I get 2, and I add 6, I get 8. 8, 2 is the new point. So you can see that it's actually very easy to transform. State the domain and range of the function in question 5s. Okay. This is now got the same range. So the domain is XER, and the range is y is bigger or equal to 0. It's the same as a normal parabola. This, same thing. Nothing's changed. This, the domain hasn't changed, but the range has been elevated by 1. So it now goes from 0 is smaller or equal to y is smaller or equal to 2. If you don't believe me, plug it into your Desmos. This one, the asymptote has been raised by 3. So horizontal asymptote, so y cannot be equal to 3, and x cannot be equal to 0. But other than that, YER and XER. This one, as I said, the bottom asymptote is still y is 0, so y is bigger than 0, and XER. And this one has been moved, multiplied by half, and moved to the right by 6. Fortunately, the normal limits are 0, 0. And all that happened was that new starting point is 6, 0. So that means x is bigger or equal to 6, and y is still bigger or equal to 0 because it wasn't raised up or down. If you don't believe me, just punch them in the Desmos and you'll see the ranges for sure. Graph the parent function of this, and then transform it. So I don't know if I'm going to graph it. I strongly suggest you do using the techniques, but let's look at the transformations. So if you look at 2 to the x, 2 to the x is going to have one major point. It's going to have 1, 0. And, it's going to have 0, 1 rather. And it's going to have 1, whatever the base is. And there's some other points that you should learn. For instance, when it's 2, it's going to be 2, 4. So there's 3 good points. Let's look at the transformations here. All my x values are multiplied by a third, and then add 1. And all my y values are multiplied by -2, and then add 4. So then you just take each one. So if I take each one of these, and I take my x value and multiply it by a third and add 1, I get 1. If I take my y value and multiply it by -2, I get -2, and add 4, I get 2. So my new point for this one is 1, 2. Then for this one, when I multiply by third, I get a third, and I add 1. I get 1 1/3. And when I take 2 and I multiply by -2, I get -4. And then when I add 4, I get 0. So 1 1/3, 0 is my new point. And then when this one I multiply it by a third, I get 2/3. And when I add 1, I get 1 2/3. And when 4 I multiply by -2, I get -8. And then I add 4, I get -4. So this is my new point. And notice that this will cause a reflection in the y-axis, so you're looking at something that's sort of going down, but then it's also raised by 4. And you're going to have a stretch and a compression, and the whole thing is moved to the right by 1 and raised by 4. So that's how you would describe it. But essentially, it's getting flipped in the x-axis because of this minus. Then it's going to be 4 higher because of this +4. And then it's going to be moved 1 to the right because of this -1. I would Desmos it. I ask you to draw it. And then I'd also ask you to put it in Desmos. Now, notice this last one. They want you to state the equation of the new one. Now, let's see if we get this one right. So the original equation looks like this. So if we rewrite it, we're going to get -2 out front. And then my x values are multiplied by 3. So that's still going to be a 3. And then I got 2. And then you just put x -1 up here. And that's like that. And +4. So this equation should produce the same thing as that. Let's try that out using Desmos. So here's our base equation. Here's our transformation. Let's do f of x instead up here. And we're going to do our g of x here. And we're just going to apply all the transformations. And I believe it was f. And then it was it 3? was x minus 1, and then it was elevated by 4. Did I get those right? Minus 2 in front, a 3, x minus 1, and then a 4. Yeah, I got it right. So we're going to zoom in on it. So there we go. See how I said it would flip? And then here's the new asymptote up top. And here's the original asymptote at the bottom. I'm going to just make them both black. Okay, so notice the purple one indeed flipped upside down and then it raised. Let's get rid of that plus 4 so that you can see it more accurately. See, it flipped in the x-axis, and then when I added plus 4, it went above. Now let's see if I got the equation right. I said the equation is going to be minus 2, 3, and should be brackets here too. And let's see if I got that right. I hope I did. I'll look silly if I didn't. I'm saying it's minus 2, open brackets, 3, open brackets, 2 to the power of x minus 1. Notice those don't really change. Close, and then add 4. I didn't get it right. 3. Let's see, what did I get wrong? I believe I have to have the 3 in here, multiplying it. So I totally got it wrong. And plus 4. What did I get wrong there? So pardon me. 2 to the power of x. All my x values and multiplied by 3. Oh, I know what I got wrong here. The 3 doesn't go there. It goes up here by the x. And I've got to put this in its own special bracket. My bad. So now if I turn that color on, off, you can see it matches the purple. And notice that I ended up putting the 3 up here, which essentially turned it into another y transformation when it really has to go beside your x. So that was my bad. And I think I even made that mistake in writing it out here. Yeah, this 3 here should actually go right up here. And there we go. You notice that the numbers are still the same. It's just where you put them in the actual equation. But if I turn this color on and off, I can see it matches the purple. So I got it right. And that's good for now. Let's see if I have time to do any of these other ones. Oh, I don't. Let me just run out and turn off my cooking, and you can fiddle around with Desmos. Only be 10 seconds. Okay, so I have time. So graph of y is equal to square root of x is stretched vertically by a factor of 3, reflected in the x-axis, shifted 5 down, 5 units to the right, determine the equation. Okay. So this is just using words instead of visuals. And trust me, every student has trouble with words. And to be honest, as I've said before, sometimes the wording is incorrect because they don't do the proper step. So they want the determine the equation from the transformations. So stretch vertically is a y factor. So right away we're just going to do all our y's because it's a lot easier. Keep it outside the square root, therefore it'll be a y. It's shifted to the right by 5. There's no downward shift, so there's no d. To do shift to the right by 5, we put a minus 5 by the x. And that will shift it to the right by 5. And then there's a reflection in the x-axis, which you'd be tempted to put minus 1 here by the x. But reflections in the x-axis are done out here. And you'll see that again if you fiddle more with Desmos. So I think I got it all. 3 reflected in the x-axis, shift to the unit by 5. There you go. So that's the new drawing. It's been reflected in the x-axis, stretched by vertically by 3, phase shifted to the right by 5 units by putting a -5 there. Relatively easy. So they're asking you to practice this point transformation. It's pretty important because you're doing it a lot. And so you just got to figure out x's and y's. So here's the x's. There's an x, so you simply add 2 to all your x's and multiply all your y's by 3. So if I add 2 to the x here, I get 3. If I multiply 8 by 3, I get 24. So the new point for this one is 3, 24. Let's go to B. So they just make it more and more complicated as they go. So let's just do it like this now. This is an x, and this is an x, and that's a y. So all my x values get multiplied by 1/2 and subtract 1, the opposite, and all my y values subtract 4. So I'll put x values here. Lovely. There we go. So if I take the original point of 1, 8, and I multiply it by 1/2, I get 1/2, and then I subtract 1, I get -1/2 is my new x value. If I take 8 and I subtract 4, I get that. So there you go. That's the new point. So let's look at this new one. So this is a y because it's outside of the f, and that's a y because it's outside the bracket. And that is an x. So that means all my x values are multiplied by -1, and all my y values are multiplied by -2, and subtract 7. And remember, yes, the normal thing is reciprocal, but the reciprocal of -1 is still -1. So if I multiply my x value by -1, I get -1. And if I multiply my y value by -2, I get -16. And then subtract 7 rather, I get -23. So that's my new point for this transformation, from this to that. Okay, let's do the next one. This one's relatively simple. This is a y, and then it's just x and x. So all my x values are multiplied by 1/4, not 4, and then subtract 1, not add. And all my y values are multiplied by -1, which means that 1 times 1/4 is 1/4, and then subtract 1 is -3/4. You'll get used to that. And then 8 multiplied by -1 is -8. And that's it. That's the new coordinate from this to that with this transformation. These are just 2 reflections. So you see this one's just a reflection in the x and the y axis, which just means I multiply my coordinate x value by -1 and the y values by -1. And I get -8, -1, -8. And that's the new coordinate of this one. These are the easiest ones to do when it's just -1, -1. And then this last one has quite a few. They're making it tough. You know, they try to get harder and harder in what they do. So I'm going to do, these are all the y's. These are all the y's, and these are the x's. So they got everything in there. So my x values are multiplied not by 0.5, but by 2, which is the reciprocal of 0.5, and then subtract 3, don't add 3. And my y values, they gave the same things to confuse you, are multiplied by 1/2, and then add 3. So they tried to make you confused with this one. So if I take my x and multiply it by 2, I get 2, and then subtract 3, I get -1. And if I take my 8 and multiply it by 1/2, I get 4, and when I add 3, I get 7. So my new point is -1, 7. Given this, find the domain and range of each of the new ones. new transformations? Well, it helps if you understand that this is this function, and it starts at 0, 0, and its domain is x is bigger or equal to 0. It's one of the few that has a limit on the domain, and y is bigger or equal to 0. And then look at the transformations. This whole thing has been shifted to the right, which means the whole graph is shifted to the right. That's what that plus 2 means, which means its domain has been shifted to the right. So now the domain becomes x is bigger or equal to 2, and y is the same. Don't believe me? Put it into Desmos. What about this one? Well, when there's a stretch, the domain doesn't really change, only on the shifts. So this range went up by 4, and this domain went to the right by 1. So now the new domain is x is bigger or equal to 1, and y is bigger or equal to 4. Now this can get tricky if there's reflections. Reflections mess that all up. So we'll keep an eye open for reflections. So that's the new domain and range of that one. Here's a reflection here. Okay, let's look at it carefully. The reflection is in front of the x, the negative, which means we have a reflection in the y values, which means x is no longer bigger or equal to 0. This reflection sends all the x's in the other direction. So x is smaller or equal to 0. If you don't believe me, plug that in. And then all the y values were raised by 1, which means y is still bigger or equal to 1. Let's test that out. Let's test that out. Square root of x, and then g is equal to the minus is equal to f minus x, and then I think plus, what did I say, plus 2? So see, all my x values are now on this side, so x is now smaller or equal to 0, and all my y values have been raised. You can see with that minus here. What if I'd put the minus in front? Well, that would have been a reflection in the x-axis like that. So all my y values are now down below, not my x values. And if I'd raised it by 2, now my y values are smaller than 2. So it's kind of weird. So you got to be really careful of the reflections. And here they give you a super complicated one, right? Here we go. So ignore the stretches. The stretches will not affect the domain, but any reflections in the x-axis will. Now, fortunately, there's no reflections, and that's just been lowered. So all my y values have been lowered by 3, and all my x values have moved to the right by 5, which means my new domain is x is bigger or equal to 5, and my new range is x is bigger or equal to minus 3. If there had been reflections, this would have gotten a lot trickier if there had been some minuses in there. The stretches surprisingly don't do anything to the domain and range most of the time, only for sine curves and curves that have a max and min. I don't know if there's other curves that I forgot. But anyway, that's that one. Let's look at 11. Greg thinks the graphs of y is equal to 5 and y are the same. Okay, let's see. Greg is incorrect. No, Greg might be correct. No, Greg is incorrect. Because look what he's done there. This has just become that in the bracket. If I factor out 5 from this, I have to divide each thing by 5. What's 5x squared? Divided by 5x squared by 5, it's x squared. So that's correct there. I get a 5 comma x squared. But the second thing, when I divide this by 5 to factor out a 5, I get minus 3 1/5. So if I were to factor out 5 from here to create this situation, that's what I get. So in reality, for it to be the same, this would have had to have been, let's see, what number, 15? Yeah, no, this number over here would have had to have been minus 15 for this to work. Or this would have had to have been 3 over 5 for this to work. So no, they are not the same. Greg smokes marijuana. All right, next. Let's see. Oh, no, I don't think I'm going to do that. So this essentially moved the entire graph of this to the right by 1. And this reflected the entire graph in the x-axis. Do I really have to do it? And this is a cubic. It's going to look like that. It's going to move to the right by 1, and then it's going to flip upside down. X cubed minus 3x squared. Squared, and then this I'm just going to move the whole thing to the right by 1. And then this I'm going to, did I reflect the G or the F? That's reflecting the original. There. So let's turn them off one by one. So how do these compare? Reflection in the x-axis, of course. How do these compare? Shifted to the left by 1. Right? That's how they compare. So you can see the translations did exactly as you would expect. Weird question. Consider the parent function has a t beside it, so I probably won't do it. Consider the parent function parabola. Describe the transformation that would produce this. Okay, well, that's a stretch of 4, vertical stretch of 4. If it was a horizontal thing, you'd see this. You'd see the 4 inside the bracket with x. When they write it like that, it's outside the bracket. Describe the transformation that produces the equation this. Okay. That is a horizontal compression of a half because it's inside the bracket. They do produce the same thing, and that's simply because one thing's stretch is another thing's compression. When I stretch something vertically, I can also create the same thing by compressing horizontally. So it kind of makes sense. Especially when you expand this. Let's do it algebraically. What is 2x squared? It's 2x times 2x. What is 2x times 2x? It's 4x squared. So you can see that this is the same as that. This has just been written inside the square. But you can see algebraically, they're the same thing. Since 2x in brackets squared is the same as that, and that's the same as that, it's clear why these graphs are the same, just written differently. And that's how we show it algebraically. Use a flowchart? No way, man. I don't flowchart for nobody. Okay. Use a flowchart. Show the sequence and type of transformations required to transfer this graph into this. Well, you can just use that formula that I gave you, the Desmos tool. This point has been, let's find the original point. So this is a good example. They're giving you the end point and not the beginning point. So, some mysterious point called xy went through the transformations and came out as 3, 6, which means we need to find the transformations. So there's a y transformation there, and there's an x transformation there. So that means the transformation that x and y went through is x got subtracted, x was subtracted by 1, and it became a 3, and it means that y was multiplied by 2, and then subtracted 4, and it became a 6. So if we write that algebraically, we can actually figure it out much easier. So if I took x and subtract 1, and I got 3, how do I get x all alone? I add 1 to both sides. That's algebra. So x must have been 4. So that means the x up here was 4. If y was multiplied by 2, and then you subtracted 4, and you got 6, let's start by adding 4 to both sides. I get 2y is equal to 10. Let's divide both sides by 2. And I get y is equal to 5, which means y started with 5. Now, if you take this original point, you want to make sure, and you run it through these transformations, you will get indeed the point. 5 multiplied by 2, subtract 4, does indeed become 6. You can see that 4, 5 is the original point, but you have to do it in this weird step and then use your algebra to solve the original. You can also reverse this process, and you can take your 6, you can add 4, that's 10, and then divide by 2, that'll give you 5. You can take your 3 and add 1, and you'll get 4. But visually, this is an easier way to do it. And the last one, don't know if I'm going to do it. Describe the transformations that produce that. Okay, we have an x compression of a third and a translation 2 to the left. The graph of f is produced by shifting 6 units to the left and then compressing the graph by a third because it's not factored correctly. So you can see this is one of the tricky things I said they do. So the actual factoring of this is you have to factor out 3 inside of that graph. And you get x plus 2, which turns out to be the same as this. So they just didn't factor this properly. Using x squared as the parent function, graph the transformation described in part A and B and show the result. No, I don't have to, actually. I'll let you do it. You just simply multiply all your x values by 3 and then add 2. And then you, if you want, like the second one is stupid. I wouldn't even bother. Because I've just proven algebraically that it's the same formula. And that's it. Hope that was helpful. It certainly wasn't as short as I anticipated.